All right, hello everyone. This is our first tutorial lecture on the use of ANSYS, this numerical simulation software. And in this tutorial, we're gonna simulate a coil. But before we start, let me say a few words about the ANSYS itself. So the ANSYS is a powerful software tool which is widely used for electromagnetic numerical simulations, right? And ANSYS provides solutions to complex electromagnetic problems by breaking them down into smaller, more manageable calculations. Okay, so one of the primary approaches used in ANSYS for electromagnetic simulations is the finite element method, or FEM. Okay, so this method involves dividing a large problem into smaller, simpler parts called finite elements. And you can imagine this like a large electromagnetic field puzzle, and FEM breaks this puzzle into small pieces, solves each piece in the puzzle, and then assembles them back together to understand the whole picture. Okay. So this method is particularly useful for dealing with complex geometries and materials, making it go-to choice for many engineering applications. So the other approaches used in ANSYS is boundary element method, method of moments, which is well suited for problems involving the conducting surfaces or wires, for example, for antennas. Finite difference time domain method, or FDTD, particularly useful for analyzing fields in transient in the time domain. ANSYS also combines, it combines all these effects with sophisticated algorithms and user-friendly interfaces, which makes it very powerful for both research and academia. And ANSYS is one of the most popular and most widely used numerical simulation software out there. So, as I said, in this first tutorial, we're gonna simulate the coils. We're gonna simulate first one coil and then a coupling of two coils. And simulating coils it's particularly important, especially in our course on electrical engineering, for several reasons. First, coils being fundamental components in many electrical devices, they play a crucial role in wide range of applications, from transformers and motors to inductors and antennas, of course. And simulation of coils helps in understanding and optimizing the electromagnetic behavior of their electromagnetic behavior, which is essential for many applications, right? On the other hand, simulating coils in ANSYS provides valuable insights into the electromagnetic design and provides an excellent way to understand the basic elements of the interface of the program, of the interface and the operations in the program. For example, these drawings, the Boolean operations, transformations, as we will see today. So so if you engage in the coil simulations using ANSYS, you basically you will essentially navigating through various fundamental features and functionalities of this software. So we simulate coils in this solver, which is called Maxwell 3D. So I can initiate this Maxwell 3D solver either from this area above, or by inserting this Maxwell 3D project in the project manager area over here. Okay, so I'm gonna use the second approach and insert Maxwell 3D design. Maxwell 3D design. So first of all, I need to check the solution type. Okay, and by default, the solution type is magnetostatic, and this is exactly the solution type we're gonna use in this tutorial. But for other tutorials, the first step you do check or change the solution type of your project. Okay, so magnetostatic project is good to go for this tutorial. So then I can save this project. Of course, I can give it a name, for example, like a coil. Already exists, so I can coil, maybe coil 1 in my case. Okay, and I can also rename this Maxwell 3D design to give it a particular name. So no need for this one for this project. All right, so the first we do, so basically the logic of working in ANSYS is to follow these items here in the solver, in the project, right? So the first line, the first item here indicates the 3D components, which is basically indicates that we should draw the structure, right? Draw the design of our virtual system, right? So in this tutorial, we're gonna draw the coil, or like a helix, and the helix you can in order to draw the helix, we go to draw and then user defined primitive and segmented helix and polygon helix. Okay, so it's gonna be a helix composed of like a segments forming a polygon. All right, so polygon helix. After clicking this button, choosing the helix, we're getting this pop-up window with the basically geometrical parameters of the helix. All right, so each item gets the description here on the right side of this table. Okay, so it gets description, the value, the unit of the value, and the name of it. So the first one we're going to change is the number of cross section of the polygon segment. So this is basically the number of sides of the cross section of the wire, the cross section of the wire that forms the helix. Okay, so in our case it's gonna be circle, the circular wire. So I'm gonna put 0 for the circle. So next, the polygon radius. I'm gonna parameterize this parameter with r, for example, r wire. Okay, so r wire, and it suggests me to give a particular value for this parameter. I'm gonna put 2. Double check that units indicates millimeters and unit type indicates length, but I still have to put millimeters here in values to like ensure that this value gonna be 2 millimeters. Double check that you always, especially for the dimensions, that you always put this, especially for the lengths, for this unit elements like lengths, radius, diameter, height, width. So that double check that you always put the dimension, either millimeter, centimeter, or nanometer, to enforce the program to use exactly this dimension. Okay, sometimes if you don't put these millimeters, the program uses other maybe dimensions by default. So double check that and click OK. So now I see that polygon radius gets this parameter, which is for now 2 millimeters, which is indicated in the evaluated value. All right, so next one is the helix radius, which is basically the radius of our coil. Okay, and I'm gonna also parameterize this one by naming it RC by R coil, and let's put 10 millimeters for now, just to start. So since we parameterized these parameters, we can change them easily from the geometrical properties. Radius change. So the radius change indicates the change of the radius of the coil along its line, right? So we have no radius change in this case. So we leave it 0. The pitch. So next, the pitch. So the pitch is the distance between the centers of the each turn, right? So it's a distance between the turns, between the centers of the turns, and it's gonna be a little bit larger than the double radius of the wire. So I put 2 times r w and plus some small gap between the wires. So let's put maybe something 0.1, and I also put millimeters here. So number of turns. So for the number of turns, let's put maybe 5. For now, segments per turn. The larger this number of segments, the closer the shape of the coil to the perfect round wire, right? So, but for the sake of feasibility of the simulation, we can put this number smaller, for example 20. Okay, and this is basically it. I can click OK and get my coil ready. Okay, so as I created this object, it immediately appears here in the model, in the solids, and in vacuum. So this coil is made of vacuum, and in ANSYS, all the elements, they are separated by these folders according to their material. So for now, the material of this coil is vacuum, so that's why it is now in the vacuum section. Right, but I can, of course, change the material parameters of this coil from vacuum, and I'm gonna use copper. So to do so, I go to this material and then edit. Okay, and here I search for copper, and double check that this is the copper with the finite bulk conductivity and the relative permittivity very close to 1, which indicates basically that this material has no magnetic properties, right? So I click OK, and I also can change the color of this coil. For example, I know that the copper is somewhat orange-ish, okay, and also double check that this element is within our, is included in our model. Okay, so if I turn off this checking mark, okay, so I will exclude this model from the geometry. So sometimes we need to exclude some elements from the project. For example, when we draw like a plane, just to represent the field distribution over this plane, it's definitely must be not included in the project. Okay, so in those cases we have to exclude the elements. So our coil, of course, is the part of the model. I click OK, apply, and OK. Okay, so this is my coil made of copper now, as indicated by the new name of this folder, copper. All right, so what's next? We draw the model, okay, and oh, of course, this is just the part of the model, because this is the coil and I need to drive the current in this coil somehow. Okay, so I need to add some kind of wire connectors to this coil. And in order to do so, we gonna use this element line in the draw section. Okay, so I choose line and navigate to exactly the center of the face of this plane here. Okay, so I find this circle. So the circle indicates that I am exactly in the center of it, and I click once. And clicking once, it puts the first point in this segmented line. Okay, so the first segment gonna be somewhat parallel to the next turn, to the wire of the next turn. So it's gonna be like this. So double check it's not triangle, because triangle connects the edges. Okay, so please make sure that this dot is kind of quadratic shape, right? So I click once, and it puts the second point of the segmented line, and then I put the last point somewhere here out of the coil, somewhat parallel to the axis X. Okay, so no need to to be precise at this moment, because we're gonna change the coordinates of these dots. And now I double click for the second dot, for the second end of this line, and this way I get this double segmented line that we're gonna turn into a connector for the coil. All right, so after that I observe this line, polyline 1 appeared in the model section of the project, and the both segments of the line appears here, and if I activate one or another one, it shows me by this bold black color. Okay, so now I'm gonna change the coordinates of the first segment. Okay, so the first point is the point of the center. I'm gonna leave it unchanged, but for the second point, I copy the coordinates of the first one and insert it here. Okay, and then I want to make this segment of the line parallel to the y-axis. So I change this y coordinate here, for example, to 4. Maybe 4 is too much, maybe 3. Double check it's in millimeters. Okay, and this way I ensure that this line is parallel to the next turn of the coil and parallel to the y-axis, and I click OK. So next I choose the second segment of the line, and notice that the first point is changed automatically. Okay, so I also copy these coordinates and insert to the second point. And now I want to change only the coordinate x. Okay, so I want to make this second segment of the line like very long, and I can put something like maybe 100 to make sure it's like long enough. And I change only sorry, I need to, yeah, positive 100, right? So it will be sufficiently long, and also this way it will be parallel to the coordinate x. So I click OK, and it shows me perfectly parallel segment of the line, parallel to the coordinate x, and lies in the plane of perpendicular to the coil, right, in this xy plane. So for now, this is just a line without any material parameters, because this line doesn't belong to any materials, right? We need to turn it into a wire. It can be done by clicking on the name of this line and then navigating to the type in the properties here, and then choosing, for example, circle for the circular wire. Okay. Then I need to change the width of this wire and, for example, make it 1 millimeter. Okay. And this wire automatically gets the material by default, which is vacuum. Okay, and let's change this material to copper. So since we already used copper, it appears in the material list. So I click copper. From this list, change the color, for example, to this orange one, and okay. So now this is the first wire of our coil. So exactly the same way I create the second terminal for our coil. Okay, so let me do it a little bit quicker. So first point, second point, third point, change the first one. So now y is negative, let's put -3. Okay. Okay. In the second segment, the first point automatically changed. I copy this one, insert to the point 2, and make x also 100. Apply. Okay. Next, change the type to the circle. Get it. Assign it 1 millimeter width, and change the material to copper, and also change the color of it. Okay, so this is the second wire. The second wire. So now now I need to draw a box around this around the structure, and we're gonna use this box, which is gonna be made of vacuum or air. We will use this box as the modeling area, so we will model the structure inside this box. So usually by default, for this purpose, you create this region by using this command here, create region. But if I use this one, if I use create region, it will include these long wires automatically as the part of the simulation area. So I don't want to do so. I'm gonna draw the box around this coil and then cut away the extra pieces of these connectors, of these wires. Okay, so I can arrange the coil in this plane. Okay, then choose the box, and let's draw the box of roughly this size in the XY plane, and I have a call. Let me. Okay, the second size of this box. Again, no need to be like precise because we're gonna change the parameters of this box. To do so, I double click this command create box, right? And for the position of the box, so but the position of the box indicates the center of the box, and I'm gonna make one size of the box parameterized also to be equal to L box. Okay, so it's gonna be minus L B over 2. Okay, because that's center here. Minus L B over 2, minus B over 2. Click, and so for the unit type, it says none. I don't like none, so I'm gonna search for the length, for the millimeters. Okay, and then let's make the size of this box, for example, 100 millimeters. 100 millimeters. I click apply, but the box appears somewhere out of the simulation area. That's because I need to change this X size to L box, Y L box, and Z also L box, apply. Okay, so this is my box. I don't like that this box is opaque for now, and I have to change that by double clicking the box. And I can change the color, but the color is no need to change that. I change the transparency now, so from the completely opaque to completely 100% transparent box. Click OK, apply. So this way now I only see the edges of the box, but not the box itself, not the size, not the sides of the box. So I don't like that my coil is oriented like asymmetrically in this box. So I still have to shift it along the X or along the Z direction. So let me change the origin of this box by plus maybe 20 millimeters. Oops, 20. So there is the problem. So if I put 20, it doesn't understand what it is. So I indicate 20 millimeters. Oops, 20 millimeters is too much, maybe 10 millimeters. 10 millimeters is perfectly enough. So now the coil is perfectly in the center of this box. Okay. So, and I'm gonna simulate the area inside this box. Okay, so this is my simulation region. So next, I created the helix and the polylines separately, and now the program doesn't understand that this is the single element of the project, and I'm gonna unite them. So I select all these three elements and then navigate to the Boolean operations over here and click unite these elements. Okay, so now this element, so now the program understands that this is one single element, so that this wire is connected to the coil, and then the coil is connected to the second wire. Okay, so everything outside of this box, I don't need that. So I'm gonna cut away these parts. And here is the trick here. I can draw another box in this attached to the first one. So this way, this box is the size of the box appears in the wrong plane, right? So I right-click the mouse and then change the grid plane from XY to XY to XZ plane. Okay, and this way I can do the first side, and then I double check that the third dimension is chosen in a way that it includes the rest of the wires perfectly. And I click OK, and it creates this the second box. So now I can select the second box and Polygon Helix and navigate to the Boolean operations and subtract. So I click subtract, and I need to change the order. So I subtract the box 2 as indicated by this minus over here. So my blank part is the helix with the wires, right? And the two parts, which is the box 2. Okay, so I subtract the box 2 from the Polygon Helix. Click OK. Okay, it removes the box with the extra parts of the wires. Okay. So for now I don't need this box, and I can click it, and but before doing that, let's double check that we've got these two areas here and here, which indicates that the box lies perfectly at the wires and by the side of the box. Okay. So now I can click the box and hide it from the area view. All right. So according to this project manager, the next section is the boundaries. But for this problem, we don't really need the boundaries, as the boundary we will use this box around the helix. Okay, so the next one is the excitations, and we're gonna drive this coil by the constant current or DC current excitation source connected to these areas here, to these faces of the wires. And in order to be able to select just the face of this wire, I navigate to this selection mode and change it from the object to face. Okay, so this way I can select only the face of the wire. I select this face and then right click and do assign excitation and current. Okay, so this is gonna be the current one. Let's name it I in or let's say I1 in, because this is going to be the first coil, and it's inner current, or the current that flows in to the structure. I change this dimension to ampere and make it, for example, 1 ampere, and the type can be, for example, stranded, and and click OK. All right, so now I navigate to the second phase, the second wire, activated, then assign excitation current 1 ampere, 1 ampere, I1 out, stranded, but the direction of this current still goes inside, so I have to swap the direction, okay, for the current that flows out from the current, and click OK. Okay, so this is the way how we created the excitation. The excitation sources appears in this excitation section of this project manager. So next, parameters. So in these parameters, we will need to assign the matrix. Okay, click matrix. And if you have just one current here, and we're gonna include this one to the project. Okay, so I include this current. So the including this parameter into the project will allow to ANSYS to calculate the self-inductance of the coil, and we're gonna use this parameter section, for example, when we calculate the system of two coils, to calculate the mutual inductance between two coils. And click OK. Okay, so this is the parameter. So next, the mesh. I right-click the mesh and set up the initial mesh settings. So let's set the initial mesh settings to the small numbers like this. Double check it's choosing the outer regime and click OK. So, but this is just the initial mesh settings, and now I'm gonna change the local mesh inside the box. So this way I click the box, then assign the mesh operations, and then inside the selection. Inside, because I gonna discretize, create the mesh inside this box. Okay, and then length based. So length based. So for this area around the coil, no need to create like a very dense mesh, and let's change this name, for example, box, and maximum element, for example, 15 millimeters. I think that's gonna be completely fine. Okay, so this way, after this operation, we got this local mesh for the box appeared in the mesh section. Next, I click Polygon Helix and again assign the mesh operation. And now I do on selection because this is my wire, and I want to discretize like more precisely the area of this of the wire, right? So also length and length based, and I put some number, for example 10 for now. So I want to make this project like feasible and easy solvable, so no need to like discretize it too much, and give it a name, for example, coil. Okay. Okay, so we created the mesh, the initial mesh settings, the mesh inside the box, and the mesh on the surface of the wire. So the next item here is the analysis. So we need to create the solution setup. So I right-click, add solution setup here, and so we're gonna use this adaptive setup for some number of passes. 10 is completely fine for such a problem, and percent error, it indicates 1. I suggest to put something like 5 to make it more feasible. So what else we need, or we should change? Yeah, so for in this section solver, we can enable the iterative solver that controls the accuracy of the solution. And that's basically it. I click OK. Next item is the optimetrics. So optimetrics, for example, allows us to create the different approaches or optimization approaches. The first one is the parametric sweep, when we create a list of different parameters that we parameterized, right? And then the program solves the project for the different geometrical parameters in the system. It also contains the other approaches like optimization, like swarm, and other approaches, the sensitivity analysis, like how sensitive the geometry or the project is, like to small variation of the parameters, statistical, and so on and so forth. So many designs here. For now, we can leave this one unchanged for the first project. And results, we're gonna create the results after the simulation. So this is the project is ready to be executed, but before doing that, we have to validate the project. So I click validate, and so this all green check marks indicates that the project is ready for simulation. And I click analyze all, analyze the project. Analyze the project, and it started the simulating. So let me pause the video. Okay, project is executed, and on my computer it took maybe just 2 minutes. I have maybe I don't remember how much. Maybe my computer gets 32 RAM, 32 gigabyte RAM. So I mean, it's a pretty good computer. So in my case, it took just 2 minutes. So let us, and it's executed without any errors, right? So in the case of any errors, you might get some red element here. Sometimes it happens in this kind of projects when, for example, the connection between the segments is not good, or maybe the mesh. So, for example, sometimes when you make this distance, the gap between the wires, if you make it like too small, it cannot mesh this area between the turns, and it also generates some warnings. But in our case, in this case, the project executed just fine. So the first thing we can check is the magnetic field distribution around the coil, right? To do so, I navigate to this measure planes. So these are the planes of the project: XY, XZ, and YZ planes. So I'm gonna plot the H field first in the vectoral form in the XZ plane. So activate this plane, right click, and then navigate to the fields. Choose H field, and H field in the vectoral form. Click OK, and here I do done. Okay. So this way I see perfectly the H field distribution around my coil. I see that the magnetic field is like stronger inside the coil, and it gets weaker outside of the coil, as indicated by the size and the color of the arrows. Okay, and as we discussed in the course, the magnetic field lines, they must be closed lines, right? So all the magnetic fields are closed. This one big red arrow is the simulation. Due to the simulation inaccuracy, if you improve the mesh, for example, you can get rid of this line. Alternatively, you can play around with the scale. For example, you can change the color bar values, for example, from here up to maybe, I don't know, 100. 100 is too small, maybe 1000. Yeah. So you can play around with the color bars. You can also activate the logarithmic scale. You can change the units. So for now it is ampere per meter. You can change you can select the others. The number of divisions, so you can like discretize it better. For example, you can put the number 50, apply, and this way you get more arrows, I guess. Right? Yeah. You can also change the type of the arrows. For example, lines, cylinder, umbrella, the size of the arrows. Yeah, like this. What else? Arrow tail. You can deactivate this arrow tail. Sometimes this arrow, tail less arrows look better. I particularly like this distribution, this way of the presenting magnetic fields. This is for the scale factor, right? So you can change the scale factor here, and so on, and so forth. So this is the magnetic H field in ampere per meter, but for the practical applications, we usually use the magnetic field, the B field. Let me plot this B field in the orthogonal plane, in the XY plane here, YZ plane. I activate this one, right click, fields, B field, and now I plot this magnitude of the magnetic field. Done. Okay, so this is the magnitude of the magnetic field B in Tesla. Okay, so for our coil, the magnetic field is around 2.6 by 10 to the power of minus 4. So quite weak, like less than milli Tesla magnetic field. Okay, so it's a weak field, and we also see that the magnetic field is enhanced inside, quickly drops to when we go out from the coil. So this field inaccuracy, right, because of the mesh, because of the discretization. And of course, if I improve the number of mesh cells, the picture gonna be improved. So in my case, I can simulate this one. For example, I can go to the box mesh, right click, and for example make it 10 for the maximum element length inside the box. Okay. Alternatively, I can also go to the mesh settings and improve the global mesh by changing this parameter. For example, this is 4. Okay, I can click OK, and reanalyze the same structure. Okay, I click OK, analyze all. Let me pause the video. Okay, so my better accuracy, better mesh project is executed, and I think the results are better. Of course, it took my computer just maybe 3 minutes to simulate the project, and I think if I improve the mesh further, the fields will be represented better, more like smooth around, and go, of course it's gonna take more time for simulation. For the parameters of the simulation, like GPU time, real time, and other parameters of simulation, basically the log file, right, the log report, we can navigate to results, and then locate this solution data, and click on this solution data, and then profile. And this profile, yeah, we can see all the parameters, for example, elapsed time of, yeah, roughly 3 minutes, and used memory, number of meshes, and all the parameters of the simulations. We can make a report of this, and so on. So what else? Yeah, we can also navigate to results and create the report. So let us create a magnetostatic report in the rectangular plot format. Okay. So in the parameters, we indicated the current, and this element allows us to calculate the coupling coefficient as a matrix element for the current one to the current one. Okay, so this is the this coupling coefficient corresponds to the self-inductance of the coil, or we can represent this as the inductance, self-inductance. Okay, I can choose this one and create new report, and it calculates me the 1 point, which is the value of the inductance in my case. So I can represent this result as the data table instead. Okay, because we have just one single number, so no need to represent it as a rectangular plot. Data table. Click OK again, and here is the is it coupling coefficient? No, it's something something else. Let me data table inductance, new report. Okay, so this is the inductance of my coil, which is 348 roughly nanohenry. Okay, for the parameter of the radius of the wire of 2 millimeters, and we can create the sweep, parameter sweep, by going to the optimetrics and right click here, and then add parametric sweep. So here in this parametric sweep, I add one parameter by adding add, and I'm gonna change the radius of the No, it's not good, because the changing of the radius will change the distance between the wires. So anyways, in the cases when you need to create the parameter sweep, you create the parameter here. For example, it can be from 1 millimeter to 3 millimeters with a step 1 millimeter, and then you create add, and it gets here, and you click OK, and then I get this parameter here, but for now I don't need this one, so I just delete it. All right, so this is basically the end of the first tutorial on ANSYS and its use for simulating coils. And thank you very much.